Hi everyone, can you hear me? Okay, so I hope you can hear me, right? So let's start with our discussion. Now, let me just remind you that what we were doing. So we were just discussing about stop and wait protocol, right? So we have discussed a few problems in stop and wait, like especially that when we are sending a packet, then how much time it is going to take. So for sending any packet, like it is going to take TP plus TT, right? So suppose like we will do the practice problem, but suppose if I just ask you that if you have, let me ask a question. If you have uh, TT is transmission time for packet and TT ACK, let's suppose, is transmission time for ACK and TP is your propagation delay. Then in this case, if I just ask you that how much time do you take from to send one packet? I mean, just start sending one packet and to receive the acknowledgement, right? So time between sending one packet to receive ACK. How much time you are going to take? So it is. Can anyone tell me quickly? It is going to be TT, right, for the packet transmission plus propagation delay plus TTACK, this transmission plus propagation delay, right? So it is going to take that much time, right? So this much time you are going to take just to send a packet and to receive a acknowledgement. Now, generally this TCAK is generally zero, okay, more often. So we are left with just one time, which is 2TT, sorry, 2TP plus TT, right? Two times propagation delay plus one time transmission time. We are left with just this time. So this is the time that we have in our hand. Now it is up to us that how we are utilizing this time, which means in this time are we sending just one packet, or in this time we are sending how much packet. Like it will make a lot of changes to the efficiency. Okay, so this time is very important. Some people just say it is just 2TP, okay, and some people just write TT also. I mean, do you remember I said like 1 upon 1 plus 2a? Some people do not write this 1 plus in even in standard resources, okay? So some people just take this 2TP or some people just take 2TP plus TT. So let me tell you that how we can drive the efficiency formula from here also. So basically, now you all must agree that this is the time, right? This time we have with us, right? With us. I mean, we can send as many packets as we want in this time. I mean, whatever the channel permits, not just one packet, right? Now, suppose that they say that that you are basically like out of this, you are just utilizing maybe just TT time. I mean, you are sending for just TT time. Then how many packets you can send? If you're just sending for TT time. So suppose if I just say that okay, I mean you are basically sending just one packet, which means, so let me just write, you are sending just one packet, right, in stop and wait, which means you are making use of how much time? It is as good as saying you are making use of TT time, because in TT time you can just send one packet, right? Now, which means what will the efficiency? Efficiency will be you're just making use of this much time and you have this much time in your hand. So this is your efficiency, right? Now, now there is one number that we said A, right? A was TP upon TT. So can anyone tell me what was this A quickly? This is number of packets we can send in TP time. Is this okay to everyone? See, so if I say that 5 TT, in 5 TT, how much packets you can send? You will just divide this 5 TT by TT, and you will say that okay, in 5 TT you can send 5 packets, because in 1 TT you can send 1 packet. So in 5 TT you can send 5 packets, right? So that's how you do. So basically, similarly, if I ask that in this much time, how much packet you can send, you will divide that by TT. So this is the number of packets that you can send in TP time, right? Now, what time you have in your hand? What time you have in your hand? You have 2 TP plus TT time in your hand. Right? It means what? Number of packets that you can send and you could have sent in this time, right? Number of packets we can send in this time. Can anyone tell me what it will be? It will be 1 plus 2a, right? So 1 plus 2 is the maximum number of packets we can send, right? So it will be 2 TP upon TT upon TT, which will be 1 plus 2a, right? This is the maximum number of packets we could have sent, and the number of packets we are sending is actually 1 only. So there are two interpretations of the efficiency. One is like if you are having number of packets, the maximum this many you can send, and how much you are actually sending. Similarly, if you have this much time maximum in your hand and how much you are actually utilizing, right? With respect to time also you can calculate, or maybe with this calculation, both are same, right? Now there is something called throughput, right? Throughput. So what is this throughput? Throughput is basically how much efficiently you are utilizing your bandwidth, or maybe in simple words I can say number of packets, right? Number of I mean, it depends on the unit basically, but you can say number of packets per unit time, something like this. Unit time we can send, right? Which means we can actually send. We can send. See, what is bandwidth? Bandwidth is, or okay, let me first completely talk about a little more about the throughput. So number of packets, or maybe you can say number of bytes, number of bits in per unit time. I mean, it depends on your unit of throughput, but you can also say number of bytes per second, something like this, right? I mean, number of bytes per second you can send. Basically, it's not like that what the channel can do. Channel can do like equal to the bandwidth. So basically, throughput is like how much we are actually utilizing the channel. So number of packets you can send per unit time, number of bytes you can send per unit of time, like that. And what is bandwidth? Bandwidth is in Mbps, if you remember, in Mbps, right? Or maybe either capital B or small b, does not matter because it depends on the unit. Let's suppose Mbps. Then it means this many, let's suppose it is let's suppose it is 5 Mbps. What does this mean? That 5 MB data we can be like, I mean, this is our like this much is the channel capacity, like 5 MB data per second could have sent with this channel per second. Right? You're getting my point? So basically, bandwidth is telling you that how much channel capacity, what is the capacity of channel. Throughput is telling you what you're actually doing. So what is the relationship between bandwidth and throughput? Let's just see. See, how much time you have. You have 1 plus, sorry, not 1 plus. You have how much time you have in your hand? So we have 2 TT, 2 TP plus TT time, right? Now, in this time, how much data you could send? Okay, in this time, which means like if this is the time is available with us, then how much data we can send? It is basically bandwidth into that much time. I mean, bandwidth is telling you that in 1 second you can send 5 MB. So in, let's suppose this is a second, then in these many seconds, how much you can send, right? So this is the maximum data that you can send. So basically in this much time, this is the maximum data you can send, right? So this is the maximum. Right? Are you getting me? See, what I'm saying, that if your bandwidth is, let's suppose 5 Mbps, which means that your channel can send the data with the 5 MB per second, then it means, and let's suppose it is also in the second, this time is also in the second, then it means I can say that, okay, if it is 5 Mbps, then in 1 second I can send 5 MB, then in these many seconds, how much I can send? This much data I can send, right? This is the maximum data I can send. Okay. Now, this is also called bandwidth delay product. What is bandwidth delay product? It is basically saying what is the maximum data that you can send. So this is the maximum, this is the maximum data that you can send, right? Now, let's just do one thing. Let's just try to convert this into A. I mean, 1 plus 2A or like that, right? So let's just see if I can convert that to A. So this is the maximum data that you can send. Suppose the data length, okay, this is in the bytes, right? Because bandwidth is in the bytes, so that's why this is in the bytes, in bytes. Suppose the data length is L bytes, okay? Suppose data length is L bytes. Now tell me, what is the maximum number of packets you can send? Maximum number of packets. I mean, data means packet length basically. Okay. So this is packet length. Maximum number of packets we can send is equal to these many bytes we can send L bytes of packet. Then what you need to do? You need to divide that with L. Right? Is this okay to everyone? Let me know if you are with me. Yes, Ekta, that is correct. So you need to divide with the L. So basically this much is the maximum number of packets you can send. Okay. So bandwidth into 2TP plus TT upon L. This is the maximum number of packets you can send. Let's just see what is this number. So what is this number? This is basically bandwidth upon L, or maybe this TP. This is the propagation time, which is distance upon velocity, and this is length upon bandwidth, right? So I think if you multiply bandwidth upon L to this, then you will be getting 1. And this is actually, okay, this is actually just a 1 upon TT, right? So let me just write this way. So see, TT is L upon bandwidth. So that's why bandwidth upon L is 1 upon TT, right? So maybe I can just write in this way. This is 1 upon TT into multiplication of 2TP plus TT, right? Which is 1 plus 2A, right? So this is the maximum number of packets you can send. I think earlier also we got the same number. So this 1 plus 2A is the maximum number of packets. In number of packets we can send in this time. I mean, this is the time that you have. In this time you can send at max these many packets, right? So basically, either you come up with this 1 plus 2A with bandwidth delay product, or I mean, it is just like you have this much time. In this much time, how many packets you can send? So maybe you can divide by TT. Or maybe you can directly, you can also say that, okay, in this much time, how much data we can send? In terms of data, in terms of byte, if you want to calculate, you can multiply by bandwidth, right? So basically, if you just directly want to calculate in terms of number of packets, In this much time, how many number of packets you can send? Divide by TT, right? That will tell you how many numbers you can, how many number of packets you can send. In case if you're interested in getting number of bytes you can send, you can multiply by bandwidth, because both are the same thing. Even if you convert that to like if you divide that by L, if you convert number of packets, this is number of bytes, and if you convert that to number of packets, then you will be getting the same answer. So are you all convinced that what is this 1 plus 2a? So the final picture of 1 plus 2a is this. See, this is sender, this is receiver, and this is the A number of packets that you can send. These are the A number of packets that the channel can hold at any point in time, right? A is the maximum number of packets the channel can hold. And then this is again A. So 2A is basically, I mean, A at any point in time, in this direction, only A packets it can hold. And in this direction also A packets it can hold when it is sending. So basically, like you can say that you are sending one packet, right? So 1 plus 2A packets also you can send. So basically total 1 plus 2A packets you can send. Some people just say only 2A packets you can send. I mean, the channel can hold maximum A packets here, A packets here. So you can send 2A packets. So basically A is the number of packets the channel can hold at max at one point in time. Why? Because one bit is going to take how much time from reach to one end to another end? This is TT. So TP, right? In this time, how much packets you can send? This much. So this is just A. So basically, when this bit is going from here to here, when this bit is going from here to here, till this time, you must have pushed A number of packets here. So the channel capacity is basically A. Channel cannot hold more than A packets at one point in time. Okay. So some people use 1 plus 2A, some people use 2A. You can use anything. I mean, on the options, it will be just one of them. Okay. So coming to this throughput is basically number of packets per unit we are actually sending. Okay, we are actually sending. You can say something like this. Per unit time we are actually sending. Okay. So what will the throughput? How much we are actually sending? We are sending just one packet, right? So you can say, maybe let me write in terms of bytes, number of bytes we are sending per second. We are a number of bytes. So what I'm interested in here now, we are interested in, my interest is basically, let's suppose, let me write a question. How many number of bytes or how many bytes we are actually sending in 1 second? Can anyone calculate this? How many bytes we are actually sending in 1 second? This is what throughput is. Okay, this is throughput. We are sending one packet. We are sending L bytes in maybe you can say 2 TP plus TT time, right? We are sending L bytes in this time. What I want to know that how many bytes, how many number of bytes we are sending in just one time. So in this much time we are sending L bytes. In one time, how much bytes we are sending? So this is, I mean, in this much second. Okay, I mean, in these seconds, let's suppose this in seconds. In these seconds, I'm sending L bytes. It means my throughput is L bytes in these seconds, right? This will be in bytes per second. Because we are sending L bytes in these seconds. So this is my throughput. Let me know if that is fine to everyone. Or there is any doubt. Now let's just do one thing. Let's just try to match this throughput with the bandwidth. So what is the throughput that we have just came up with? So throughput is this. Throughput means the number of bytes we are sending in just 1 second. So this is my throughput. Okay. Now what we could have actually sent if bandwidth is, let's suppose, I mean, whatever is your bandwidth, you can actually send that much. So if bandwidth is 5 Mbps, then you can send 5 MB per second, but you are sending actually lesser, maybe. So let's just see that what is the relationship between throughput and bandwidth now, right? So now you understood what is throughput, like what is this time, and like basically we have this much maximum time. Okay, this much maximum time. In this much time, whatever I'm doing, it is related to efficiency and everything, right? So in this much time, if I'm just sending one packet, if I'm just utilizing TT time, okay, if I'm just utilizing TT time, this will be my efficiency. Okay. Similarly, in this much time, I can send 1 plus 2 a packet, but I'm just sending one packet. This is my efficiency. So both are equal. Similarly, I can say, so this is the efficiency, right? This is the efficiency. Similarly, I can say in this much time, I'm sending just L bytes. So this is my throughput, something like that. So now let's just relate this this number with the bandwidth. So let me say, see, this is my efficiency. So what you can do, you can just write this L. I mean, you can just maybe this TT is how much? This TT is, I mean, this is length upon bandwidth, right? This is transmission time. So basically, you can relate this with the bandwidth using this. This is length upon bandwidth. So you can say this is length upon bandwidth. So now, okay, so what you can do, you can basically multiply by the bandwidth. If you, in this efficiency, if you multiply the bandwidth, you will be getting the throughput, isn't it? So in this efficiency, if you just multiply by the bandwidth, then this L will get remain, and then that's the throughput only. So this is throughput. Yes, KS, that is correct. Right. So have you understood how we are coming up with this formula instead of just remembering this formula? I mean, you should get some feeling that why this formula is like how this formula is basically derived. I mean, students just remember this formula, but we should actually know that how, like, I mean, what is the picture behind this formula? So basically, I mean, that's very easy. Like how throughput is actually how much we are actually doing, right? Which is related to like this much data we are actually sending, and in this much time. So that's the throughput, and that will be like if you just compare with the efficiency and bandwidth, then it will be efficiency, like how much efficiently we are utilizing the bandwidth. So basically, if you are utilizing with the 100% efficiency, then throughput is just bandwidth. I mean, it is great if you are utilizing with the 100% efficiency. So if the efficiency is 1, then throughput and bandwidth both are equal, right? If efficiency is 1, throughput is equal to bandwidth. Similarly, if the efficiency is let's suppose lesser, then throughput will be lesser. Okay. So, okay. So I hope you understood all of this. Now let's just move to some of the problems. So in stop and wait, we are going to solve some problems. Then we will move to the sliding window protocol, right? Yeah. So flow control method, practice questions. So let's do this question. What they are saying, in stop and wait, every 4th packet is lost. If 8 packets are being sent, then find the number of packets. So what they're saying, every 4th packet is lost, which means, let's suppose you're sending packet number 1, packet number 2, packet number 3, packet number 4. Then what will get lost? This 4th packet will get lost. Now, it is quite easy to solve this question in the sense that like when we go back end, then it will be a little tricky, but for the stop and wait, it is actually quite easy in the sense that if this 4th is lost, then you just need to retransmit the 4th one only, because you are going to wait and there will be a retransmission timeout that will get expired, and then you are going to retransmit this 4th only. Is this okay to everyone? Right. Now you are going to send 5, right? I mean, so every 4th packet is lost, so this will get lost, and then after that 1 2 3 5 6 7, okay, this 7 will get lost. Why this 7? Because now this is again 4th one, right? This is lost. Now you start your counting from here, 1 2 3 4. Now this is again lost. Now if this is lost, you are going to retransmit it. Now if you are going to retransmit it, are you going to retransmit anything else? No, because you have only sent this 7, so that's why you are only going to retransmit this 7. Now 7 8 9 10, what they're saying, 8 packets are being sent. Okay, so they are only sending 8 packets. So they're only sending these 8 packets. So to send 8 packets, how many packets you are extra sending? 2 packets you are extra sending. So that's why you will say that find the number of packets that are actually sent. So basically total number of packets that you are sending is 10. Okay. ठीक है. Okay. So now let's solve this question. Okay, most of the question I have taken from the MIT MIT one HTML page was there, one course is there for the MIT data communication course or something. So most of the questions I have taken from this MIT book, MIT page. Okay. So what this question is saying, a sender S and a receiver R are connected over a network that has K links. Each that has K links that can each lose packets. Okay, so the links are not 100% reliable, which means there might be a packet lost. Link I has a packet loss of rate pi in one direction from S to R and qi in another other direction R to S. So basically there are multiple links, and if you are sending a packet from here to here, then there is a probability pi that the packet will get lost. Similarly, if you are sending from here to here, there is a probability qi that the packet will get lost. Assume that each packet on a link is received or lost independent of other packet. So there is no relation between two packets. I mean, if one packet is getting dropped, it doesn't mean that other packet will get dropped or something. So these are independent. Okay, independent probabilities are there. Right now, what they are asking, suppose that the probability that a data packet does not reach R. So this is S, this is R. When sent S is P. Okay, so they are saying that there is a probability. Maybe I can go to the next page. So there is a probability P which is saying that data packet does not reach to from S to R, right? So P is the probability that it is saying that from S to R you are not able to reach, and Q is the probability that the ACK packet sent by R does not reach to S. So Q is the probability that some ACK is not getting not getting to from R to S, and P is the total probability that it is not getting reached from S to R. So what is the probability that it is not getting reached from S to just immediate? What is the probability it is not getting S to not getting reached from S to just immediate? This one, just PI, right? I mean P1. What is the probability it is not getting reached from P1 this by this to this? Maybe P2. So you can multiply with P2. So basically this with this probability, the packet will not reach from here to here, right? So okay, the packet will not reach, and the packet should not reach from here to here also, right? So this is the probability by which you can say the packet will not reach from here to here. Similarly, what is the probability the packet will not reach from S to R? You will multiply all of this P on the way. So see this answer. You are going to multiply all the p's. Okay, what they are saying, the probability that it can, suppose the probability that the data packet does not reach R when the when sent R is P. So they are asking about P and Q. So the final expression is this one. Okay, so they have subtracted one. What is this PI? PI is the packet loss rate. Link I has a packet loss rate. Packet will get lost with the probability PI. Yeah. So okay. So 1 minus PI will be the packet should not get lost from here. Okay, this is the probability. This is the probability that packet is actually reaching, right? And then they have subtracted 1 minus that. Now, what was the wrong with our method that we were doing? So what is the wrong with this? The packet should not reach from here to here, and then packet should not reach from here to here like this. And ultimately, packet will not reach. What is wrong with this method? Can anyone tell me? Okay, so maybe let's go to the next page. So let's consider only the two links in between. Okay. P1 is the probability that packet get drop here. P2 is the probability that packet get drop here. Which means if packet is reaching from here to here, then 1 minus P1. I want the let me ask that, okay, if I want the packet to reach from here to here, then what is the probability? This will be the probability. Packet should reach from here to here, and it should reach from here to here also. And packet doesn't reach. So this is the probability that packet reaches from S to R, and the packet doesn't reach from S to R. This is the probability. That is okay, right? But why we cannot say that packet doesn't reach from S to R is that packet not reach from S to, let's suppose this intermediate A, okay, which is P1, and then packet should not reach from A to R, which is P2. What is wrong with this? Yeah. So if Alap is saying if packet is not reaching using this P1, then it won't reach P2 either way. So basically, what is wrong with this? Like what you are saying, if packet, you are saying that with this probability packet is not reaching, then if packet is not reaching like with this probability, then like, I mean, you need to basically do more analysis. You cannot directly multiply by P2. Reason being is that you will say if packet is not reaching here, then how you are saying that it is it is here? Like, I mean, how you are multiplying with the P2? You're getting my point? If packet is not reaching from here to here with this much probability, then how you're directly multiplying by the P2 by saying, okay, it will not reach from here to here. So maybe we can do a little more analysis here. Let's just try to do it. I'm not sure if I like that will be a successful experiment, but let's just try doing it. So basically, okay, let's just take two cases. With P1 probability packet reaches, with 1 minus P1, so P1 probability packet does not reaches, with 1 minus P1 probability packet reaches, right? Now, if packet does not reach, then it automatically does not reach from S to R, right? So it does not reach from S to R. So this is the probability that it does not reach from S to R. So P1 plus some other probability, right? So what is some other probability? It reaches from S to A, and then P2, 1 minus P2, it does not reaches from A to R. So plus 1 minus P1 into P2. So this should be the probability that it does not reaches from S to R, right? I mean, it does not reaches from S to A, or it reaches from S to A, but it does not reaches from A to R. You getting my point? So I think these two numbers should be same. Do you want to do it quickly? So this will be 1 minus P1, right? Minus P2 plus P1 P2. So this 1 will get cancelled out. So this will be P1 plus P2 minus P1 P2, right? P1 plus P2 minus P1. Yeah. So these two numbers are actually same. So basically, you need to be more careful in these kind of questions, right? So one of the option will definitely be something like this, P1 into P2, but P1 into P2 is not the correct answer. Okay. So packet, I mean, instead of that, maybe you must have done this kind of questions in the combinatorics, in the discrete mathematics, that 1 minus the whole thing, right? Whole thing, probability of whole thing. So basically, it is if you want to, if you're getting confused, then think in some other direction. Think in the reverse direction. That, okay, what is the probability that it reaches? Then I will just subtract 1 minus that probability. Okay. Okay, great. So this is first question. Let's just go to the second one. Okay. So these are the other questions, B and C. Let's just check these questions also. So what they're saying, if, let me just a second. If all PIs are equal to some value alpha, okay, which is very lesser than 1, much lesser than 1, then what is the what is P defined above? Approximately equal to. So P basically, that's the same quantity P. So they are saying that if this PIs are very less, then what is this P? Okay, 1 second. So what they're saying, if all PIs are very less, that is equal to some alpha, then what is P approximately equal to? Which means it will be 1 minus alpha power, sorry, 1 minus alpha power K, right? P equal to this. Now, how you can approximate it? I think 1 minus alpha power k is just 1 minus alpha k. Can anyone tell me how? If alpha is very lesser than 1? Do you remember the binomial theorem? Yes, yes, Alap, that is correct. So if you just expand this, actually you do not need to remember it. I mean, you do not need to do all of this. You can actually remember this, that if this alpha is very, very lesser than 1, then it is just 1 plus x power n. In general, 1 plus x power n. Actually, I remember this from my 12th class. Okay, I just got to remember here now. So this 1 plus x power n is just 1 plus nx if x is very lesser than 1. Reason being is that if you expand this by the binomial theorem, this will be 1 plus nx plus, I think, nc2. It is like that, right? nc2 1 power, I mean, this will be the powers of x square or something, right? So this will be powers of x. So we can always ignore the powers of x after it, right? So if you expand this by the binomial theorem, you can always ignore the powers of x. So that is why you can approximate this 1 plus nx, 1 plus x power n as 1 plus nx. Anyway, so alpha k is the answer. Let me check. Yeah. So suppose S and R uses the stop and wait protocol to communicate what the expected number of the transmissions of a packet before S can send the next packet in the sequence. Okay. What is the expected number of transmission of a packet before S can? So basically they are saying that what is the expected number of packets that you need to send just to send one packet. Okay. So just to send one packet, what is the expected number of packets that you need to send? If the probability of losing something is, let's suppose, P, or probability of success, let's suppose probability of success sending is P, then what is the expected number of trials that you need to make? 1 upon P, right? This is the expected number of trials. But here, what is the probability of success? Probability of sending? This number, right? This number is the probability of success. So basically you can say 1 minus P. So 1 minus P here currently in this particular question, this 1 minus P is the probability of sending one packet to sending one packet from one side to other is equal to 1 minus P. So what is the expected number of packets you need to send? 1 upon 1 minus P, right? Where P is this number, or 1 minus P is this number. Okay. So yeah, is this correct, or there is something wrong? I think we need to also consider Q, because this is just sending this. We need to consider Q also. So you will say the probability of successful sending. Successful sending is not just 1 minus P. It is I think 1 minus P. Can anyone correct it quickly? 1 minus P into something. So successfully sending the packet and then successfully receiving the acknowledgement also. So what should be the answer? 1 minus P into 1 minus Q, right? So 1 minus P into 1 minus Q. So basically, this with this much probability, you are actually saying, sender is actually saying that, okay, I have actually sent the packet. So that's why the expected number of packets that you need to send just to send one packet is 1 upon 1 minus P into 1 minus Q. Okay. Yeah. Is this okay to everyone? That why I've written 1 minus P into 1 minus Q? Because like I want the sender to get confirmation that, okay, the packet has been actually sent. So with this probability, sender will say that, okay, the packet is actually sent, which means this is the probability of success, which means these many number of trials you will be needing to send just one packet. Okay. Now let's go to the next page. Again, this question I have taken from the same course, which is MIT course. Okay. So let's just see this question, what they are saying. A sender A and the receiver B are communicating using stop and wait protocol that we studied in this course 6.02. There are n links on the path between A and B, with each with the data rate of r bits per second. Okay, so it is actually the bandwidth. I mean, bandwidth in the sense like it is the maximum data flow that the channel can have. So there are n links in between A and B. And each is having some bandwidth of r bits per second. The size of the data packet is S bits. So basically the length is given to be S bits. And the size of an acknowledgement, okay, acknowledgement size is also given. So packet length and ACK length is also given to be K bits. Each link has a physical distance of d meters. So distance is given d meters. And the speed of signal propagation over each link is c meters. So velocity is given c meters per second. Okay. This is d meters. The total processing time experienced by data packets and its acknowledgement is TP. Okay, processing time. So there are also processing time. So currently till this point we have not done the this processing time in the picture, because like we were saying that okay, let's take it negligible, let's take the acknowledgement length also negligible, but they are saying that okay, in between there might be some processing. So they are saying the total processing time, let's just keep it TP for the data packet and its acknowledgement. So which means that whatever you are sending, then you are receiving in the total duration. Okay, in the total of sending, receiving one packet and receiving one packet, it's just TP. TP is processing time here. ACKs are drivers in the same link as the data packet, except that in the opposite direction. The propagation time and the data rate are same in both the directions of the link. There is no queuing delay in the network. Okay, queuing delay is not there. So generally we take the queuing delay, processing time, these are all zeros. So they're saying there is no queuing delay. Each link has a packet loss probability of P. Okay, so the packet can get lost with the probability of P. So each link is saying the packet can get lost with the probability of P, and the data rate is R bits per second, or the bandwidth is R bits per second, right? What are the following four quantities in terms of given parameter? The transmission time for the for a data packet on a link between A and B. So they're asking about the transmission time. So let me just remove these things. Okay. So can you calculate the transmission time meanwhile? So they're asking about the transmission time. So these are the details that are given to us. Transmission time will be transmission time for a data packet on one link between A and B. So on any link between A and B, it will be length upon bandwidth, right? So for the data packet they're asking, so that's why you can say length. What is the length? S bits upon what is the bandwidth? R. So this is the transmission time, right? I hope that is fine to everyone. So let's just go to the next thing. What they're asking as a next thing, they are saying the propagation time, okay, for the data packets across the links in between A and B. So propagation time, let's just have the propagation time here. So what will the propagation time? It should be distance upon velocity, right? So propagation time for the data packets across n links between A and B. Between just one, what is the propagation time? Distance, what is the distance here? D meters upon velocity c. So I think capital D upon small c, right? So this will be the propagation time for one link only, but they are asking for the n links, so you need to multiply by the n. So the answer will be, let me write the answer also. Answer here will be n into D upon c, right? Is this okay to everyone? This is my answer. Now let's just go to the next question. What they're asking is that the round trip time. Okay, let me copy this one. Yeah. So they are saying the round trip time between A and B. What will the round trip time between A and B? is okay, and then they have defined also round trip time, that the round trip time is defined like this, that the RTT is defined as the elapsed time or the total time between the start of the transmission of a data packet and the completion of the receipt of the ACK, which means they are saying the total time when you think about the start of the transmission till the point you receive the ACK, right? This is the total time that they are asking. What is the total time? The start of the transmission, that's what they are calling it round trip time. So can you tell me what are the things you are doing? You're transmitting the data. So this will be the transmission time was what? S upon R, right? You're transmitting the data. Then you are having the propagation. So how many propagations? You are having n propagations. So n d upon c. Also, this is just for the data packet. Okay. Also, there are how much delay? Processing delay, right? So processing delay for the data and the ACK I will at the end. Now for the ACK, what is the transmission time? ACK is having some length here, k bits, right? So for ACK, this is the transmission time. ACK will also take this much propagation time, and then this is the time for the data. This is the time for ACK, and then you are going to add one more quantity, which is processing time for all of the ACK and everything. Like that's what they said. Like, so TP is the processing time for everything. So I think this is the answer, right? Let me quickly check. NS upon R and NK upon R. Yeah, this is the answer. Okay. So what is the D? D is saying probability that the data packet sent by A will reach B. What is the probability that if you are sending from A, it will reach B? I think that's easy one. Tell me quickly. If you are sending some data packet, this the P is the probability of losing the data, right? Loss probability. Yeah, P is the probability, which is loss probability. Okay. So if this is the loss probability, then what you will say? What is the probability that it will reach from A to B? It should reach from A to this. It should reach from A to this. So 1 minus P power n, right? This is the probability. Okay. So what is the route? Okay. Should I do this C again? So C is saying that what is the total time? They have defined the RTT such that RTT defines the elapsed time between the start of the transmission of the data packet and the completion of the receipt of the ACK sent in the response of the data packet. Okay, this is some misspelling data packets. Right? Reception by the receiver. Okay. So total time they're asking. So what you will do? You will transmit the data. You will transmit the packet, and then it will get propagated through the N links. You will transmit the ACK. It will get propagated through the N links. Plus, this is TP. They are saying it's a processing delay. Okay, for everything, for data packets between N links. So this is the processing delay between all N links. I mean, processing delay of all N links. Right? Of yeah, this is for the N links of data and ACK both. For data and ACK both. Okay. Now let's move to the next question. This question I have taken from MIT. So what they are saying, consider two nodes A and B. Suppose the network path from A to B has a bandwidth of 5 KB per second, 5000 bytes per second, and a propagation time of 120 milliseconds. The path in the reverse direction from B to A has a bandwidth of this much and the propagation time of this much. Let the data packet size is this and this, okay. Give a numeric expression of the throughput that A can achieve in transmitting to B using stop and wait. So they are asking about the throughput. Let's just solve this question. Consider two nodes A and B. Suppose the network path from A to B has a bandwidth they have given to be 5 KB per second, and the propagation time they have given to be 120 millisecond. The path in the reverse direction from B to A has a bandwidth of 10 KB. Okay, so this is from A to B. So they are saying there are different bandwidths. So from B to A, there is a different bandwidth. That might be taking a different route, and then they are saying that that is having a bandwidth of 10 KB. bandwidth of 10 kb per second, and the propagation delay here is obviously okay, not obviously, but yeah, most probably lesser. Let the data packets have a size including all headers of this much. Okay, so the data is having this much size, 500 bytes, and the acknowledgement size, so L, length of data is given to us is 500 bytes, and length of acknowledgement is given to us is 100 bytes. Now they're asking about the throughput. Give a numerical expression of the throughput that A can achieve in transmitting to B using stop and wait. You can treat 500 bytes data transfer as transferring permanent bytes of useful data. Okay, anyway, so basically you want to transfer this 500 bytes. So how much throughput you will be achieving? You can calculate the efficiency, and then based on that you can calculate the throughput, right? Efficiency into bandwidth is just throughput. So let me do in that way. From A to B, what is the efficiency? 1 upon 1 plus 2A. 2A means propagation delay upon the transmission time. 120 millisecond upon transmission time. So you need to calculate the transmission time here first, which will be, this is 500 bytes. So this is 500 length upon bandwidth, right? 5 into 10 to the power 3. Then these many seconds. And then if you want to convert that to milliseconds, then you can multiply by the 10 to the power 3 to convert it to milliseconds. So these many milliseconds. So this will be, I think, 100. Right? So the efficiency will be 1 upon 1 plus, this is 1.2. Okay, so 1 upon 3.4. This is 2.4, and then this is 3.4. So this is efficiency. So that is why throughput will be, what is the throughput? Efficiency into bandwidth. So that's how you can calculate the throughput. Let me check the answer. So yeah, they are saying the transmission time is this. So they have calculated the transmission time to be 100 milliseconds. So this is 100 milliseconds is the transmission time. The transmission time for the acknowledgement, okay, from B to A, if you want, you can calculate, but I don't think we need it for this question. The total propagation time is 80 plus. Okay, 1 second. Given a numerical expression for A that can achieve in transmitting to B using stop and wait. Okay, sorry. So yeah, this is some nice question. So basically you need to check the throughput. Throughput is basically how much packets you can actually send, right? Now let's not use this formula directly, because in this formula I have ignored the length of acknowledgement and all. So basically let's just do some manual calculation. Okay, so what is the throughput? Throughput is basically we are sending just one packet, or we are just utilizing one time, this TT time. Okay, first we need to find out the efficiency. We are utilizing was just TT time. Out of how much time can you tell me? Out of TT plus TP plus time of acknowledgement, because they've given the length of this. Generally the length we take is 0, so that's why we do not take the transmission time of this, and then plus TP. I think this is the total time that we have in our hand, and out of this we are just utilizing TT time. Is this okay to everyone? This is the efficiency that we have. Yes. Yeah. So let's just calculate this efficiency. So basically, it will be, like, you can say it will be 1 upon 1 plus 2A plus something like this T acknowledgement upon TP, something like this, right? So let's just calculate transmission time for the acknowledgement. What is the transmission time for the acknowledgement? It will be length upon bandwidth. So it is basically 10 milliseconds. If you do it, it will be 10 milliseconds. Now you can calculate the efficiency. Efficiency will be transmission time upon transmission time for this into 2 into what is the propagation delay? Propagation delay is also divided into two parts, not just one, because it is not TP plus TP, it will be TP-ACK basically, right? This is for the data, this is for the ACK. So here, this is transmission time for the data is 100, propagation delay for the data is 120, plus transmission time for ACK is 10, Propagation time for the ACK is, I think 80, it was 80, right? So that's how you need to calculate the efficiency, right? Is this okay to everyone? So basically you need to take it very carefully, that how to calculate the efficiency is that how much time total we have, time to transmit the data, time to send it here, then time to transmit the acknowledgement, time to send it here. So basically we have the total time is TT plus TP. And then similarly for the ACK also, there are different parameters that they have given. Okay, this propagation also different. Okay, not only transmission time, they've given the propagation delay also different. So this is the total time that we have in our hand. But out of that, how much we are actually utilizing? We are just utilizing TT time, because we are just transmitting, and then after the transmission, sender is sitting ideal in the stop and wait. So that's the total time. So it is 200, 300, and then 310. So 100 upon 310. And then what is the bandwidth? Bandwidth is 5 kb. Okay. Yeah, this is also interesting, right? So it is a 5 kb from A to B. It is 10 kbps from B to A. So how to make use of this? If there are two bandwidths that are given to us, how to calculate the throughput? What they're asking is basically throughput that A can achieve in transmitting to B. So let's just see here. This is 3110, and then they are directly multiplying with the stop and wait. A can send the data per RTT. So the throughput it can achieve is 500 bytes. Yeah, they are actually, I mean, either you can make use of efficiency basically, or maybe you can say that this is the total time. In this total time, you're just sending the 500 bytes, right? Yes, that is correct. So this is the total time that you have in your hand, and these in this total time, you're sending 500 bytes. So basically 500 bytes upon this much total time that you have in your hand. So that's how you can calculate the throughput. But can you calculate using bandwidth also? Which means these two bandwidths are given to us, this one and this one. Can you calculate the throughput using bandwidth? Okay. So generally we say that efficiency into bandwidth is throughput, but here the bandwidth is also not fixed. Should we take the bandwidth from A to B only? Okay. So what does throughput mean basically? Like we are saying with respect to sender, right? I mean, how much data we can send in per second. So this is, I think we should take only with respect to this one, because this is the bandwidth that A to B has, and this is the efficiency. Efficiency means, like I'm saying that this much time I'm utilizing out of whole time. So basically this much time I'm utilizing, and if I want to send the data, then I could have sent, see, this is efficiency, which is saying 100 upon 310, right? What does this mean? Like how we have calculated this efficiency? We said that this is the time that we have in our hand, and out of that, this much we are utilizing. So basically, sorry, this is the time we have in our hand, the total time, and this is useful time. I mean, this is the time actually we are utilizing, right? Let's suppose these are the millisecond or something. So let's suppose this is the millisecond. So we are saying that 100 millisecond we are utilizing out of the 310 milliseconds. So if you want to send the data, then from A to B, we are saying that there is a bandwidth of 5 kilobytes per second. In 1 second, you could have sent 5 kilobytes data, right? So basically, like for the throughput with respect to the data, like how much data you could have sent. So we will be only considering this one way, I mean, this from A to B bandwidth. Why we are not considering B to A is because, like, B to A is giving you some extra time, that is okay. but that is not for the data, right? I mean, you are sending the data from A to B only. B to A is having some different route, and that route is taken by the AC keys. But you want to send the data only, right? I mean, from A perspective, you want to send the data. So A will check the bandwidth of this, which is 5 kilobytes per second, right? I mean, this channel, this A B to A could be having more bandwidth, could be having lesser bandwidth, right? We don't care. I mean, it is just giving us extra time to send the data, right? This thing, if this is, let's suppose, lesser or more, then maybe it is giving lesser time or more time, but it is just giving me extra time, right? Giving us extra time to send more data. I mean, because the acknowledgement is, let's suppose, coming very slow, then it means we just got the extra time to send the more data. So basically, it is just giving this extra time. Here, this bandwidth is irrelevant to calculate the throughput. Reason being is that we want to send the data on this link. So this bandwidth will be calculated. And how much time we have? Like, this is the total time we have, and this is the time we are utilizing. So what will the bandwidth? So in this total time, which is 310, right? Like, out of this total time, I'm utilizing this time. So which means the throughput will be, this is 5 kb per second. So how much data I'm sending per second? So basically, efficiency into bandwidth. So I will say that this is the bandwidth, and I'm only this much efficient. So I'm sending this much data per second, right? Using this link A to B. Okay. So if you want to calculate the throughput, like, I mean, those complicated questions might not come, but if you want to calculate the throughput, you can directly go with that approach, that okay, length upon I mean, how much data you are sending, like total data you are sending in how much time. So basically, you can do this approach, that you are actually sending 500 bytes, because you're just sending one packet in how much time. So this is because the one packet in stop and wait. In how much time? 310 milliseconds, right? Okay. Let's calculate this B. What this B is asking. Give a numeric expression for the size of the window in terms of, okay, this is for sliding window. We will do it after the sliding window, right? Okay. I think these are related to some sliding window protocol. Okay. I think these are related to only stop and wait. So let's just see this. What is the maximum rate that A can achieve? So throughput we have just calculated that A can have that much throughput. What is the maximum rate that A can achieve? It is just bandwidth, right? I mean, in stop and wait, it cannot cross the throughput, obviously, like whatever is the throughput, but in general, it is just bandwidth. So A can achieve 5 kb per second, because this is the bandwidth. So when the window is greater than or equal to bandwidth into delay, okay, that we will see later. But yeah, maximum it can have the bandwidth. Yes. Now let's just see D. If the bandwidth of the path from B to A drops to 100 bytes per second. So earlier I think it was 10 kilobytes per second. So from here they are saying it just has dropped to 100 bytes per second, and can A still achieve the same rate? Okay, tell me. Maximum rate, yes, it can achieve, but the throughput will be same or lesser or greater. If the bandwidth is decreasing, then what do you think? If the bandwidth, let's suppose if I just ask that from A to B, there was some bandwidth, and B to A there was some bandwidth, and now I'm reducing this bandwidth, then do you think the throughput of A will decrease or increase? I mean, there will be any change on the throughput or not? If this bandwidth is decreasing, then the transmission time will be increasing, right? For the TACK, transmission time for the ACK will be increasing. So I will be getting, see, it is length upon bandwidth, right? If it is decreasing, then transmission time will get increased. So I will be getting more time here. If I'm getting more time, and I'm just utilizing the fixed time, which is TT. So basically the denominator will be more even, right? This is TT. the denominator will be more, so the efficiency will even decrease. If I talk about the efficiency, then it will decrease. You got my point? So basically, if we are going to reduce this bandwidth, if this bandwidth gets reduced, then this time of ACK will get increased, and I will be having more time. Okay, and I'm just bound to utilize this time. If I'm having more time, so there's basically here is a term which is TACK, right? So the terms here are, this is time of transmission, time of propagation plus transmission time of ACK plus propagation time of ACK. Now, if this is increasing, I'm actually having more time, and I'm just bound to utilize this much time. So efficiency will even decrease. Right? Okay. So if you talk about the efficiency, then it will decrease. When the bandwidth in the reverse cycle drops, source actually not only does the transmission time of the acknowledgement goes up, but even more critically, the windows can advance. Okay. So window thing we will see a little later. But yeah, I hope you understood that what I want to say here. The efficiency will even decrease because I'm having more time, and I don't want more time, right? Okay. So now let's solve this gate PYQ on a wireless link of the probability. I think you can do it maybe. Okay, we did it already, right? Yeah. That was a 300. So we did it in last class also. So a channel with the bit rate, so it is of stop and wait, right? Minimum frame size, yeah. So the channel has a bit rate of 4 kilobytes per second. One propagation delay, one way propagation delay is 20 milliseconds. Maximum rate is just bandwidth. I mean, maximum is just hypothetically that you can do. So throughput is very bounded. I mean, if you follow the protocol, then the throughput is very bounded. You cannot utilize more than TT time, right? So you cannot have more efficiency. But the maximum, if hypothetically I tell you, then it is just bandwidth. Maximum rate is just bandwidth. Okay. That hypothetically throughput is actually, that's what you are actually doing. Okay, so here, I mean, that's the reality. There is no imagination that okay, maximum that you could do this, minimum you could do this. Throughput is actually what we are actually doing. A channel of a bit rate has bit rate of 4 kbps. So basically bandwidth is given to you 4 kilobits, okay, times power 3 bits per second, and one way propagation delay of 20 milliseconds. So propagation time is also given to be 20 milliseconds. The channel uses a stop and wait protocol. The transmission time of the acknowledgement frame is negligible. So, okay, transmission time for the acknowledgement is negligible. To get the channel efficiency of at least 50%, the minimum frame size should be. So, they want the efficiency to be greater than or equal to 50%, which is 1/2. So, which means this efficiency is 1/1 plus 2a is greater than or equal to 1/2. So, from here, you can calculate that what should be your a. This is 1 plus 2a is lesser than or equal to 2. 2a is lesser than or equal to 1. A should be lesser than or equal to 1. So a is your TP upon TT. So which means like 20 upon TT should be lesser than or equal to 1. So from here you can find out that TT is greater than or equal to 20. So TT is greater than or equal to 20 means what is this TT? Length upon bandwidth, right? So length is greater than or equal to 20 into bandwidth, this one. So these many bits you will be having in the bits. This 20 is in the millisecond. It is in a second. So let me convert that to also second. So basically it will be 80 bits. 80 bits. We believe the answer. I mean, minimum it should be 80 bits. 160, how? Just okay. Have I missed 2 somewhere? This is greater than or equal to 1/2. This should be lesser than or equal to 2. 2a is lesser than or equal to 1. Okay, a is lesser than or equal to 1/2. A is lesser than or equal to 1/2, which means this is lesser than or equal to 1/2. Yeah, I will need to multiply by the 2 also. So basically it is 160 bits. So D is the answer. Okay. So let's just understand this question a little more carefully. So what they're saying is that they want the efficiency to be at least 50%, right? And then if you want to increase the in the stop and wait, what is in your hand? See, in the stop and wait, if you want to increase the efficiency, then what you can do? To increase the efficiency, you should be just keep on sending the data, then only you can increase the efficiency. See, efficiency is saying that how much time you are utilizing just to, you know, in this whole time. This is what efficiency is saying, right? So if this transmission time is smaller, then you are utilizing a smaller time. If this transmission time is very big, which means, let's suppose transmission time is so big that the moment you finish transmitting, okay, then this is the moment that this last bit is basically almost to the sender, to the receiver. Basically your transmission time is so big, then you say that, okay, my transmission is finished. By that time, this this last bit is just about to reach the receiver. Basically, you need to fill this channel, right? You need to fill this channel. So you can say that if you want to fill this channel, then you can keep on transmitting. I mean, you take your frame size too big, that you keep on transmitting. If you do not want, if you cannot send multiple packets, then send just one packet that is too big. Okay, so that's what the stop and wait is saying, that if you cannot send multiple packets to increase the efficiency, then I can send one packet. Okay, let me send one packet, but it will be too big. That's what they are saying. Okay, so if length is minimum, so if you are increasing the length, then the efficiency will get increased in case of stop and wait. Because if I'm not able to send multiple packets, then let me send just one packet, but I will send a very big packet, so that I'm little more efficient. Okay. Yeah. So now let's solve this question. Consider the sliding window protocol. Okay, so now these are the questions related to sliding window protocol. So let's just have the sliding window protocol in place. So sliding window protocol, right? The sliding window protocol is basically one theoretical idea, which means, let me write theoretical idea, which is saying that you can what you can do, you can send multiple packets in that time. So basically, why to wait for why to wait for the acknowledgement to come? You can send multiple packets by the time acknowledgement is coming. Okay, so here in this time you can send actually multiple packets. That's the sliding window idea. And then practically you can implement that in two ways. One is called go back N, another one is called selective repeat. Okay, let's just see these two protocols. So maybe you have seen the slides earlier, but let me just go to the slides. Okay, this question is basically stop and wait. So they're saying, what is bandwidth into delay product? The system can send this. Okay, you may solve these questions also, right? Okay, so let's just first see what is go back N. Now here N denotes the window size of the sender. So basically it says that you can send multiple packets by the time the first acknowledgement is coming. So allow the transmission of new packets before earlier ones are acknowledged. The sender has a window size of n packets that can be sent without acknowledgement. Okay, so you do not need to wait for the acknowledgement. You can send all of the packets, and let's just wait for the acknowledgement after sending some few packets. So okay, now let's just see that how acknowledgement works in case of go back N. Now let's suppose that you are sending some packets. Let's suppose you are sending these many packets. Then it uses basically cumulative acknowledgement, which means that receiver can send the acknowledgement for multiple packets at a time. Which means receiver, if receiver has received, let's suppose till packet number 3, then it can send, it can say that, okay, I have received till packet number 3. So it can say that, okay, acknowledgement for the packet number 3 is it can send the acknowledgement for the packet number 3. Therefore the cumulative acknowledgement mean. Okay, you might have seen the lectures already. So working for the go back N. So how does it work? Let's suppose you are sending from 0, 1, 2, 3. Okay, let's suppose you are sending this much data. Then this 0, let's suppose 0, 0, receive, 1, receive, 2, receive, 3, receive. Then this receiver will send the acknowledgement as cumulative. Okay, it may send for the individual packet, but it's better to send for the cumulative. Cumulative means that if it is saying that, okay, ACK3, it is sending the ACK3, then it means that till, like, it is receiver has basically received till data packet 2, and now it is expecting the data packet 3. Okay, So let's just see some possibilities at the sender and receiver side. For how many packets it will send one packet, that is not fixed. This is based on the timer. Okay, once the timer get expired, it will send one. It will send the acknowledgement. So how it is working? Let's suppose that you have some window and you are sending some data, right? Let's suppose it's 0, 1, 2, 3, something. You are sending 0, maybe. Okay, let's just take some of the possibilities, which is, let's suppose that this packet get lost. Let's suppose this first packet get lost, okay, which is 1. Then you are sending 2. You have sent 3. You have sent till 3, and the first packet get lost. So it will receive this 1, and then it may send the ACK. It may not send the ACK for this 0. It receives for the 0. Then after some timer, it will send the ACK, or maybe it can send the ACK for each, but still it is cumulative. Cumulative means that if this receiver is saying that ACK 3, it means it has received till 2. Okay, cumulative means this only, right? So cumulative means that if you are sending, even if you can send the ACK for each packet, but cumulative, if you are using the cumulative acknowledgement, it means that this that receiver is saying that that I have received till all the packets till this point, not just this one, because receiver window size is just 1 here. So receiver can receive only in order packets. So if 0 is coming, 0 will be accepted by the receiver. 1 is coming, but 1 get lost. So that is why 1 will not be able to reach to the receiver. Now 2 will reach to the receiver. Now receiver will accept 2 or reject 2. Receiver will reject these packets, right? Reject. And once the receiver reject these packets, then maybe after some timer, it will send that, okay, I am looking for the packet number 1. Or maybe once it receives this packet, then only it can say that, okay, see, what I'm trying to tell you, that how the receiver is going to send the ACK. Okay, so at receiver side, you can send the ACK for this immediately, maybe after some timer. Let's suppose after some timer. Okay, ACK timer. So once you send this ACK, then okay, this go back and will able to realize that, okay, this sender will say that that it has only received the 0, because ACK 1 has come, then it means it has only received the 0. No, it will retransmit this 1, 2, 3. Okay, not just 1, because sender has not like receiver has must discarded 2 and 3, right? So that is why sender will send 1, 2, and 3 again. So that's why it is called go back end. So basically what is happening here, that you are sending ACK after some timer, which is ACK 1, and sender will say that, okay, since I have just received ACK 1, that is why it must be the case that only this 1 has received. Like I'm not receiving ACK for other packets. So it will basically 0 has received, it will send the other packets, which is 1, 2, 3. Now you may send ACK from here also, right? You may send ACK at each packet also. That's not a problem. Or maybe the ACK timer can get expired anywhere in the between. Here also, okay? Here also, it can get expired anywhere in the between. Or maybe the third possibility is that it depends on the implementation, but the third possibility is that you can send ACK once this is received. See what is happening, that you are sending some packet, okay? This packet has got reached. Now this packet has failed. This packet has reached, but the receiver will not accept it. That's another story. But yeah, this packet has reached. So let's suppose this is packet number 0. This is packet number 1. This is 2. This is 3. Right? Sender has sent 0, 1, 2, 3. Now receiver will say that, okay, 0 has been accepted. I'm happy. Now since it has not accepted 1, so it will reject these 2 and 3. Is this clear to everyone? Discard. Now receiver has to send the ACK. Now what I am telling you that how receiver is sending the ACK. Maybe receiver can send ACK after some timer. Okay. So maybe let's suppose the timer is getting expired here. So receiver will send the ACK. ACK here. It will say that, okay, after some timer, or maybe it can send the ACK, and then it will say that, okay, I have received only 0. Now I'm waiting for 1. ACK 1 means I'm waiting for 1. Now sender will get to know, okay, since it has only received the 0, then it has not received the 1, then probably then it must have not received the 2 and 3 also. So it will send this whole thing. This is 1, 2, 3, right? That is okay. Like that is understood to everyone that how the sender is working. Now I'm from the receiver perspective, I'm telling you, it can send the ACK here after some timer maybe. Okay. Or maybe let's suppose if timer is too long. Let's suppose if timer is too long here, then what we can do, basically we may not wait for the timer. We can say whenever we are receiving some packet, it means most probably it means, can anyone tell me what does this mean most probably? Most probably it means that one is lost because I received 2. So at that time also I can send ACK1. Like receiver will say that okay, I'm discarding it, but I'm looking for ACK1. You getting my point? So basically, once this 2 is received, at that time, receiver will say that okay, there might be most probably there's a possibility that 1 is lost. Right? So basically, it depends on the implementation. Most probably, you can just think about it that it will wait for the timer. After timer, it will send. Okay. So whatever is the possibility, sender has to make sure that all the packets has received. Receiver will always receive in order. That's the only two things. Okay. Sender has to make sure that all packets have received. And receiver will accept in order only. Okay. So Alap is asking, how would it look like if all the packets were received? Yeah, for the normal operation, if all the packets are received, then then sender will say that okay, see here, if you are sending some packet, if all the packets are received, then you may send the acknowledgement for every packet, or maybe after some time, maybe you can complete a packet, or maybe you can say okay, after 3 I will send, maybe the count you can say that okay, after 2 packets I will send the acknowledgement. So once the acknowledgement of 4 is received, okay, acknowledgement of 4 means that these 3 packets have been accepted by the receiver. Now it will move its window to 4, 5, 6, 7 like that. So it will keep on moving the window like that. So let me just tell you normal operation, all right? So normal operation, go back in. So this is no packet lost, nothing lost, normal operation. How does the normal operation look like? It is basically just sliding the window. Right? It is sending, let's suppose 4 packets, and here you have 0, 1, 2, 3, 4, 5, 6. Let's suppose initially you are sending 0, 1, 2, 3, and then once it receives these packets, right? Once it receives these packets, now it will send the ACK. Okay, so ACK after some timer, or maybe at every moment you can send, after some timer you can send, doesn't matter. So it will send the ACK. Now once the ACK 4 is received, then only it will move the window. Or let's suppose that what is happening in between. Let's suppose that this has received here, okay, which is ACK2. Now what the sender will do? Sender will say that okay, since the ACK2 has received, which means that the sender is expecting 2 and it must have received 0, 1. So sender will slide its window, something like this. In a window, every time we have the 4 packets. So sender will slide this window like this. What does window slide mean? Window slide mean that it immediately sends this 4, 5. So the moment it receives ACK2, it will immediately send 4, 5 also. Whatever is in the window, I just send it immediately. Okay, whatever is in the window. Window means like I have sent it. So this means this is acknowledged. This is acknowledged. I just acknowledge it. This means that this is in air. I don't know what's going to happen with them. Maybe maybe like receiver will receive it. Maybe there is some lost or something. These are in air. I don't know. Or some people call it outstanding packet, and these are yet to send. Right? This is outstanding. So whenever you have the window means that those all packets have been sent. Now suppose that you receive the acknowledgement for 2, then what will happen? If you receive the acknowledgement for 2, you immediately send 6 packet. You will immediately move this window to the 6. You will immediately send the 6 packet the moment you receive the acknowledgement for 2. Okay. So this is how the normal operation look like. maybe you can watch the videos again. So now how the what are the other possibilities at the sender and receiver side? Maybe a sender is sending some data is get lost, then receiver will discard all the data and it will say that okay, send me one only like that. Then maybe after the timeout, so here also you have the timeout, right? So at the go back end, right, let me write here, timers at go back end, right? See, at the sender side, there is always a timer that is retransmission timeout, right? Timeout timer or RTO, retransmission timeout, whatever you want to call. Let me write retransmission. That is always there in stop and wait or in sliding window or anything, right? And at the receiver side here, you have a timer, which is ACK timer. Now, how do you implement cumulative ACK? Which means whenever you are getting a packet, whenever you are getting multiple packets, then how do you react to those packets in terms of the ACK? One of the option is that after a certain time, okay, maybe ACK timer, or you can have mix of them also. ACK timer, after a certain time, you are very rigid that after a certain time only I will send the ACK. Okay, this is the only criteria that you have, after a certain time only. Maybe you can say that okay, ACK timer is there, I agree, but I can also send along with that, or maybe apart from that, maybe you can have a count. I mean, ACK timer in terms of time, okay, in time. Also, you can have the ACK timer in count. Maybe after 5 packets only, I will send the ACK. Something like that, right? It is up to you. That after 5 seconds also, after 5 packets only, I will send the ACK. After let's suppose 100 milliseconds only, I will send the ACK. So something like this, right? Maybe you can send ACK at every packet. That's also fine, right? It doesn't mean it is not cumulative. Cumulative means what? That sender will understand if you are sending ACK 5. Sender will say that okay, from 0 to 4 must have been received. This is what cumulative acknowledgement means. Cumulative does not mean that we cannot send at every point. We can send at every point, right? We can send at every packet. But from the sender perspective, if I'm receiving ACK 5, then it means that from 0 to 4 has been accepted. Okay, this is what cumulative acknowledgement means. We can definitely send at every packet also. That's not a problem. Okay. And what are the other strategies you can think of to implement the cumulative timer, cumulative ACK? Maybe some mix of them, right? After ACK at every packet, maybe, or maybe you can say ACK at okay. One other strategy could be that ACK when out of order packet arrives. Which means that this packet is lost, let's suppose, and then you get this packet. Then immediately you will say that okay, you are getting the packet number 2, right? This is 012. You are getting the packet number 2, but you are not getting packet number 1. It must mean that packet number 1. I mean, most probably it means that packet number 1 is lost, right? Oh yeah, it could be delayed, but most probably it means the packet number 1 is lost. So the receiver will say that okay, let's not wait for the ACK timer. Let me immediately inform the sender that okay, packet number 1 is lost. I'm expecting packet number 1. ACK 1 means I'm expecting the packet number 1. So whenever there is some out of order packet, then also you can send the ACK, right? So this is up to the implementation, how you want to implement your ACK. Is this okay to everyone? Okay. Let me know if there is any doubt. Yeah, entire window is sent. In the window, whatever you have, let's suppose you have 0, 1, 2, 3, right? Then you will send the entire window from here. You will send the entire window. Okay. You will always send the entire window. Let's suppose you receive the acknowledgement for 0, or maybe you suddenly receive the acknowledgement for 2. Okay. You are not receiving acknowledgement since a long time. But suppose this is 0, 1, 2, 3, 4, 5, 6, Okay, so in your current window, you have just sent this, but all of the sudden, okay, you have sent this, you have not received for 0 and 1. The 0 and 1 acknowledgement has not come, but the acknowledgement for 2 has come. Then what you will do? I mean, acknowledgement for 2 means like it is receiver is asking for 2. So you will say that, okay, 0 and 1 must have been reached, right? Then only it is asking for 2. So you will immediately understand that, okay, 0 and 1 must have been reached. So you will just shift your window like this. And whatever is in the window, it means that it is in the air, which means 4 and 5 in the air. Immediately you send it. I'm assuming that you already have data to send. If you do not have data to send, then obviously you cannot send it, right? Is this okay to everyone? Okay. So 0 1 will never get 0 1. Okay, you are not understanding anything. See, you are sending 0 1 2 3 4 5 6. Suppose something like this, right? 4 5 6 7. Suppose this is your sender window or sender data packets. Now you are sending, let's suppose, from 0 to 3. Okay, which means this 0 1 2 3. Now it received 0, it received 1, and then maybe let's suppose it also received 2, and then it only sends the ACK for 2. Okay, or maybe ACK for this one. Suppose this it says that, okay, the ACK2 means now it is expecting for 2. It immediately sends, let's suppose, ACK for 2, which means it is expecting 2, and then 2 will come after some time. That's okay, but from the sender point in time, sender will say that, okay, since the 0 and 1, it is asking for ACK2, since the 0 and 1 must have been received, that is why it will immediately shift its window, and then it will immediately send 4 and 5. So whatever is in the window, I'm immediately sending it. Okay, so I'm not waiting for anything. So window means this is in air. Okay, so these are the normal operations that you have. Now, if now you can consider different scenarios. Let's suppose if some data is lost, then after timeout you can send, or maybe you receive some ACK that, okay, I mean, like there are some fast retransmission technique also that we use in TCP, that after 3 ACKs we can send, or maybe after timeout you can send. So if that is not received by the receiver, then what you can do? You can like wait for the timer, and after timeout you are going to send. No, everything will get sent, right? In the previous example. No, why you are going to send again? You are saying that you are expecting 2, so it means 0 and 1 has been received. You will just slide your window, you will wait for this acknowledgement, you will send 4 and 5, you will wait for the acknowledgement. Why you will send this 2 and 3 again? Yeah, new window is 2 3 4 5. Okay, so should I explain this properly? I mean, I thought that you must have watched the videos, but if not, then what you can do, you can watch the videos later also. No, why to resend the whole window? You are just going to slide the window, and whatever you have sent, you will send this thing, this 4 and 5, not the whole window. You are just going to slide the window because you have received it. You will say, okay, finally these has been sent. Now let me just slide my window. Let me send the 4 and 5. Let me not wait for the acknowledgement. It's just like that. I'm not waiting for the acknowledgement 2 and 3. Okay, so there might be some confusion. So basically, okay, let me quickly explain if there's a confusion that is coming to you, that how it is working. Okay, let's just see the working. It is, let's suppose, 0 1 2 3 4 5 6 7 8. Now there is no point, right? There is no point in sending 2 and 3 again. Like, you think logically, why you will send 2 and 3 again? So suppose that it has received, so whatever it has sent is basically 0 1 2 3, right? Till this point it has sent 0 1 2 3. Suppose it has received the acknowledgement for 0 only. Okay, I mean, it may receive for 1 later, but let's suppose for this point in time it has received the acknowledgement 0, means 0 has been received. What it will do? It will slide its window. It will immediately slide its window and immediately say that, okay, now my window is this. Now let me send 4 also. Right? It will not send 1 2 3 again. Like there is no point in sending 1 2 3 again. Why you will send 1 2 3 again? You have just said that okay, 0 has been received. You are not saying that 1 2 3 has not been received. You're just saying 0 has been received. So let me slide my window. Slide my window means immediately send this 4. And then it will wait for the acknowledgement. Now let's suppose the acknowledgement for 3 has come. If acknowledgement for 3 has come, so this was ACK 40. Okay. Now let's suppose, so ACK 40 will be actually ACK 1, but I'm just writing ACK 40. Okay. Now let's suppose that ACK for 3 has come. I'm just saying that 3 has been received. It means what? If I'm saying 3 has been received, then till this point everything must have been received. Then I will just immediately slide my window. Okay. If 3 has been received, I'm saying, then I will immediately slide my window to 1 2 3 4. So yeah, always I have the four data packets in my window. So it will be my window. Now, immediately I will send 5 6 7. Whatever is in the window, it is in air actually. Immediately I will send 5 6 7. Right. So the moment I will keep on receiving, I will keep on shifting my window like that. Okay. So there are different scenarios. Let's take one scenario when packet is lost. If packet is lost, then after timeout you are anyway going to send it. Okay. And yeah, so there could be many strategies in practical. Like, can you think of some other strategy? Maybe some more efficient strategy. Instead of timeout, can you do something else? So case is asking if we get ACK 5 again repeatedly. Yeah, you will not move the window till the point you get the acknowledgement for something. If you're not getting the acknowledgement, if you're saying that okay, the receiver has not received this 4, okay, if you're again and again saying the receiver has not received this 4, then after timeout you have to actually retransmit this 4. So retransmit this 4 means that you have to retransmit 4 5 6 7. Yeah, that is true. So basically, if you're retransmitting anything in the window, if you're retransmitting, let's suppose this 4, okay, then it means you have to retransmit the whole window. If you have to retransmit, yes, that is correct. Okay, so suppose at this point in time, ACK4 this 4 is not received. Like you have sent 4 5 6 7. Now you are waiting for the ACKs. If one of the ACK get received, let's suppose 4 6 has been received, then you will immediately slide the window. But suppose any of the ACK is not get received. Any of the ACK means neither 4 4 5 nor 6 4 7. Because if one of the ACK get received, you will slide this window. So now you know how to slide the window. But now let's take another case where any ACK is not received. Then after timeout, what will happen? 4 5 6 7, all of this window will get retransmitted after timeout. Yes. Because after timeout, you will say that okay, if 4 has not been received, then 5 and 6 7 must have not been received logically, right? So after timeout, yes, after timeout, the whole window will get retransmitted. After timeout. And as long as you're receiving everything fine, okay, 0 0 has been received. As long as you're receiving the ACKs, you will keep on sliding the window. The moment you do not receive the ACK, then you will wait for the timeout and then you will retransmit everything, right? So I hope you understood the working. So basically, as long as we keep on receiving the ACKs, we keep on sliding the window, right? And once we do not stop, once we don't get ACK, don't any ACK, then after timeout, we will, after timeout, what we will do? We will retransmit the whole window. Now tell me, will there be any possibility that if window is, let's suppose window is 4 5 6 7 currently, will there be any possibility that you are retransmitting only 6 7? If window is 4, 5, 6, 7, I mean, you are not sliding the window. Window is this only. So there cannot be any possibility like that, right? I mean, you have to retransmit the whole window. If you are not receiving the ACK for the outstanding packets, then you have to retransmit this 4 also. And then since the 4 has not been received, then obviously 5 also, 6 also, 7 also, right? So you keep on sliding the window. It is as easy as that. And then once you do not receive ACK, you retransmit the whole window. Okay. Now let's take the different possibilities maybe. So this is basically the crux, I can say. Now, what may so happen? Let's suppose that some of the data is getting lost. If some data is getting lost, then let's suppose that this is 0, 1, 2, 3. Okay, something like this. If this data get lost, then it will not send the ACK for this, right? So it may silently discard this too. I mean, see, it is up to you how you are implementing, right? So what do I mean by that? See, okay, let me go step by step. Let's suppose this is you have just sent this, and then you have received this 0. Okay, you have not received this one. Now, from the sender side, there is a timer. What is the timer? From the sender side, what is the timer? Timer for the packet, right? So basically, at the sender side, you have the timer, which is timer for each packet. Like for this packet, there is a timer. But let's suppose this ACK has been received to the sender, then there is no worry, and then it will immediately shift it will immediately slide its window. So let's suppose that for every packet we have the timer, and I mean, it is up to again the implementation that you can have a timer for the every packet, or maybe you can have timer for just one packet, which is first outstanding packet, because there is no point in keeping track of this. If this is getting expired, then these timers are actually useless. I mean, you are anyway going to retransmit, right? So okay, just for the simplicity, let's have the timer for each packet. Okay, so see here, I think in the videos also I have the timer for each packet. Yeah, so it actually does not matter. It depends on us that how we are implementing. Either you have the timer for each packet, Okay, for each packet we have the timer. I think this is for selective repeat. In go back and also you can have timer for each packet. Does not matter. Okay. Okay. So suppose this data is lost. Now, at the sender side, let's suppose this 0 ACK you have at the receiver side. Let's suppose you 0 ACK you sent somewhere here after some time, or maybe immediately or somewhere, right? So maybe you are sending this. Okay. Let's not worry about it, right? Now, at this sender side, what will happen? Sender will say that, okay, for each packet I have the timer, that after timeout, it will retransmit this packet, which means it will retransmit this one. And obviously it has to retransmit whatever it has retransmitted after 1, 2, 3, 4. If it is retransmitted 4 also, then 1, 2, 3, 4 like that, right? Whatever it has retransmitted after 1, it has to retransmit the whole window. So 1, 2, 3, whatever it has retransmitted, right? Transmitted earlier. So that's the one case, that after timeout you are retransmitting. What could be other case? I mean, again, I might be making it little complicated, but from the practical point of view, what you can do, you can say that, okay, let's not wait for the timer to get timeout. Maybe you can apply some other strategy. You can say that what I will do, I will not like I have the timer, right? I have the timer. I will instead of only waiting for the timer, the receiver is making it little optimized. Receiver is saying that, see, whenever I receive out of order packet, at that time also I send the ACK. I send the ACK. Okay, I'm saying, okay, ACK1, ACK1. I need one. You are sending me 2. You are sending me 3. I need one, right? So what will happen at the sender side? Sender will say that, okay, receiver is again and again saying that I need one. So why to wait for the timer, right? Why to wait for the timer? Timer is going to expire, let's suppose here, right? Let me just immediately send one, because receiver is again and again saying that I need one, something like that, right? I mean, practically you can implement it anyway. It will be given in the question. You got this idea? The second way, what I'm saying? In the second way, I'm saying that like the first is saying that you may wait for the timer. Second is saying you may not wait for the timer. Like let the receiver, if the receiver is saying that, okay, again and again I need one, then let's not wait for the timer. Let's just send this one immediately. Right? This could be some other strategy that you can use. Right? Okay, so this is just one of the possibility. When timer get expired, you will send the packet. Another could be packet is delayed. Let's suppose packet is delayed, it will discard all of this and then it will send the ACK for 2. So if packet is delayed, let's take this possibility. Okay, I will take doubts in a minute. Let me just cover another possibility. Yes, so if packet is delayed, okay, just please focus here. I will take doubt in just a minute. So which means, let's suppose you are sending some packets and one of the packet get delayed. Okay, suppose this packet is getting delayed and it is getting received here. So it will discard all of the packet in between, right? Obviously this is out of order packet. It will discard all of the packet and then it will say this is 0, this is 1, this is 2, 3, 4. Then it will say that okay, 0 has been received, 0 has been received. Now I will discard all of the packet out of order packet. These are the out of order packet for the receiver. These are out of order packet. So it will discard. Then the moment it has received this packet, it will send the ACK for this. It will say okay, ACK for 2. ACK 2 means like now I am expecting 2. Now receiver will send 2, 3, 4 again because 2, 3, 4 has been discarded. ACK for 2, if receiver is expecting 2, it means that it is expecting starting from 2 because the receiver window size is just 1. Okay. So if packet is delayed, then you will just retransmit the whole window. Like it is quite easy. I mean, here you have initially, here you have 0, 1, 2, 3, 4, 5, 6, something like this. And then 0, let's suppose 0 ACK has been received. Then the sender will say that, okay, let me move my window. So window size is, let's suppose 5. Let me move my window from 1 to 6, right? I mean, earlier it was from 0 to 5 only. Now I'm moving my window from 1 to 6 because the 0 has been received. Now it is waiting for 1 to get received. Now 1 is not received, it will wait, and after some timer, maybe it will send if the ACK has not been received, or maybe within that timer is ACK is received, then it will slide its window of 1, right? If it will slide its window of 1, and then it will say that okay, now it will retransmit this 2, 3, 4, 5, 6 because after timeout only. Okay, after timeout only it will retransmit. It will say that okay, that 2 timer has been expired. Now let me retransmit the whole window. So basically it always retransmit after timeout. I mean, this is just one of the implementation, or maybe you may not wait for the timeout. If receiver is again and again saying that okay, see, I have not received one, something like this, then also you can send before the timer expires also. I mean, it is up to the implementation part. Okay. What is the third? If ACK is delayed, and then like we can handle these kind of situations which are already given in the theory. So let's just do one thing. Maybe you can watch these videos, and then we can have one more class for this questions, right? Now let me take the doubt that you have. Okay. So doubt is if 4, 5, 6, 7 is the last window. Okay. Let's suppose there is no more data to send. Okay. Let ACK for 6 and 7 is not received. Okay. Then the whole window is retransmitted. So you are saying ACK for 4 and 5 has been received, right? ACK for 4 and 5 has been received. And for 6 and 7 it is not received. No, why you will just think logically. If sender is saying that okay, if the ACK is received, then why you will do it, right? You will only send 6 and 7 in this corner case. You will only send 6 and 7. I mean, if it has been received, then why you will retransmit it? Just think like this. Receiver is saying that okay, I have received it. Then why will sender burden the receiver again? Because receiver anyway going to discard it, and there is no need to send also, right? Okay. Yeah, new window will be just 6, 7. So do you want me to continue, or you want to take a break? I think let's just continue tomorrow. Okay. So tomorrow we can, I think it is taking a little longer than I was expecting. But anyway, let's just continue tomorrow. Okay. Okay. Thank you, everyone. Take care. Bye bye. So I will share the slides, these slides that I have just used. So the tomorrow topic will be same. Like tomorrow, I will be just solving more questions related to stop and wait, related to sliding window protocols. Right? I've taken some questions from MIT book, and I will be solving more questions tomorrow. Yeah. Thank you, everyone. Yeah, access methods, like we will cover everything. Okay. Okay. Once this topic is finished, we will cover everything.